hopefully it's good news. You will hear from Lisa again. That's not the last time that she'll be talking to you. So my name is Robert Hayes. I administer the health physics programs at NC State, both the graduate and the undergraduate. That means radiation safety and radiological protection. I am a certified health physicist by the American Board of Health Physics, which makes me an expert in these kinds of things. I've got 15 years of experience working in nuclear waste management, radiological emergency response, and now I teach these things. These are the subjects. What I'm about to show you is the stuff I do research on, the stuff that's in my classrooms that I teach, that's in the textbooks, that's standard academic content. And we'll actually see some of the stuff that I have published. I get to reference some of my own work, because most of this comes from in my own published research. And my background, after industry, I also ended up getting a number of accolades. I'm a fellow of the American Physical Society. That's the professional society for physicists, for people that love to study physics. I'm also a fellow of the Health Physics Society, Radiation Safety, Radiological Protection. And I'm also a licensed professional engineer, which means that by the national standards, when I do calculations, you can rely on my calculations for safety. Just like you would for any medical professional that's licensed, that means that you have met that pedigree of demonstrating the quality and excellence of your technical capabilities. And one of the things that I'm quite passionate about, I learned the hard way, is public outreach. So that little QR code is actually my social media channel. I'm on TikTok, where I talk about these kinds of things. But what we're about to talk about today is getting really, for me, is really just the hardcore science. The science of what I teach and do research on. And so it's not going to be as warm and fuzzy perhaps as we had, but then I'm not so good at my soft skills as other people in my team are. So here's what we're going to talk about. First off, I'm going to go over a quick review of the nuclear fuel cycle, where that comes from, the issues of nuclear waste. Like I said, I used to do this. I worked at a geological repository for transuranic waste. It was licensed in '99 by the EPA there in southeast New Mexico. We're going to talk about that, but then possibly what's going to be the best part of this lecture is radiological risk in context. Historically, people have liked that the most. That's the most insightful and informative that would allow somebody to make a proper risk-based decision. And that's really what that part will do. Then we'll look at the science for the energy landscape, and then possibly, I know somebody had mentioned this, nuclear accidents. You get to talk to somebody that's been through them. Like I said, I used to do radiological emergency response professionally. I was on the NEST, the Nuclear Emergency Support Team. My office was there at Nellis Air Force Base. We're run by the same operating contractor of the former Nevada test site. And then we'll talk about logistics, the fundamentals of logistics, and then finally the Q&A. And then hopefully a really, really yummy lunch. That would be the goal. So how does a nuclear power plant work? The simplest way to break it down is it is simply hot rocks that make steam. The thermal fuel cycle that you have with coal and oil and natural gas and geothermal is you have a heat source to boil water that makes steam. The steam expands in a turbine. That turbine spins a dynamo that makes electricity. Now there are two basic types that we have. We have a pressurized water reactor and a boiling water reactor. And what ends up happening in both of these is that you either have the secondary cycle where you boil water separate outside of the reactor, or the boiling water reactor where you boil water in the reactor. And in both of these, like I said, it makes steam to turn a turbine. And when that turbine is turned, then we have to take that very wet steam, and to put it back in the reactor to keep the cycle going, you've got to remove that heat. And to remove that heat, there are a number of ways to do it. One way is cooling towers. Another way is to have a body of water, like a lake or the ocean. Now, even those aren't required, and there are even advanced cooling towers that are out there, but you can come up with novel solutions. About 40 or 50 years ago in Arizona, we put the second largest nuclear installation in the country, Palo Verde, just outside of Phoenix, right smack dab in the middle of the Arizona desert. And where did it get its cooling water? It's all gray water from Phoenix. And they share their excess energy with cities as far away as LA and Vegas. And so whatever thermal cycle you have, you're going to have this water to remove that heat. Otherwise, you can't put it back into the heat source and boil it again so that you can make electricity. And so all thermal cycles require that to some extent. And the amount that you have really just comes down to the thermal efficiency of your heat source. The hotter your source, the less water you need. The cooler your coolant, if this is very cool, is simply Carnot efficiency, depending on the amount, the cold temperature and the hot temperature. And that ratio is really all that comes in fundamentally to decide how efficient you are in terms of using the heat and turning that into energy. The fuel cycle. The fuel cycle basically starts with the Earth. We extract the natural uranium from the Earth. We'll look at a graph later that shows just how much uranium there is. It's actually quite abundant. It's more abundant than tin. There's a lot of it, but like all geological processes, certain minerals are concentrated based on how water moves and how magma moves and so forth, and so you get different ore concentrations based on geological history. So by removing the uranium, that requires traditional mining or more advanced mining. There are multiple ways of doing it, but historically you would dig a hole and then you would mill the soil, you would leach it to separate the silica from everything else that's in there. Once you've separated out the things from the silica, then you're going to do various chemical processes to take those minerals and turn those into metals if you wanted to make metals. And uranium is very much like that in that process. Once you've got the uranium, then you're going to have to, that will be in the form of U3O8. Then you've got to convert that into a uranium hexafluoride, where we'll do enrichment. With the enrichment, then uranium hexafluoride, once it's enriched in the isotope uranium-235, that then you could do another chemical process to turn that into uranium dioxide, UO2. That UO2 would get sintered, made into those pellets that you saw some little copies of. We have some on the back tables. That goes into the fuel rods, which goes into the reactor. Once it's in the reactor, once it's up in the reactor, then we have multiple paths. The only one that we have right now that's available is that you simply throw it away. When you've only used about 5% of the energy, and then you start the process again. Now, as a nuclear engineer, what I teach my students is that as a good steward, it makes more sense to have recycling. So you don't have to come back here and keep digging up more soil. You simply reuse it. There's so much that's still there, it just makes sense to reuse it. But right now, that's really the only option that we have, is the once through, unless we decided we were going to invest in a reprocessing facility, which we don't have commercially. The only technology that we have for reprocessing in that sense is in the weapons program, so it's not available to make electricity. Whether we make another watt of electricity with nuclear fuel ever in the future, we still have this issue of the used nuclear fuel. Even if we turned off all of the nuclear power plants, we still have the issue of what are we going to do with it. Right now, it's located on site. And this puts in scale the size of these things. So these things, they are about 10 meters high. And these things can terrify people. They're this mysterious power that is who knows what. And you saw this one before, but now you can see the scale of these things. And what we're going to learn quite shortly is that if you can see the fence around these things, to try to put this in perspective, the dose rate from that fuel is a fraction of natural background. The radiation you get from nature that's already there, remember the uranium back here, it comes from the Earth. All of that radioactivity comes from the Earth. And so that's radioactive. Everything's radioactive to trace levels, literally. Everything at trace levels has radioactivity in it. It's just that if you go to the right ore, you can get more. And you can make it cost efficient by making electricity. And so the radiation that's given by these casks, because of the interior shielding, is quite low, as you saw in those photos.
Can we get copies of these slides? Is it possible to get copies of your slides?
Yes, sure.
Okay.
Yeah. And the publications upon which they're based.
Okay.
Absolutely. And so this is we showed some dummy copies right here of these fuel pellets. They are put into these cylindrical rods that go into these bundles. We have some copies of 3D printed versions back in the back row. That these get put into a canister that then goes into these casks. These casks are rather impressive engineering features. They're cooled by air cooled, so that these little holes down here allow convective heat removal. So that the heat that's inside of these, the residual heat from the radioactivity, it does heat up the canister walls, but that heating causes buoyancy in the air, which then pulls the air up to the top of these casks, and it pulls in through the bottom. So really the only maintenance you have to do is make sure that animals don't nest in there. And that you make sure that you just do visual inspections, that there aren't any cracks, that nothing has occurred due to some manufacturing error or something like that. And that's pretty much the only thing that you need to do to maintain these things. They're licensed for 40 years. You can relicense them twice for another 40 years. And they're expected to last passively for about 100. So you basically just kind of cut that in half and say, we're going to double check it just to be sure. That's typical for how we do things. Now, one of the things that I like to point out, that this is one of my favorite little statistics, is you recognize the United States has got about 20% of its electricity from nuclear energy for about 50 years. Biggest economy on the planet's ever known. Manufacturing powerhouse. 20% of our energy has come from nuclear for decades, 50 years. And all the spent fuel from all of that energy, all of that used nuclear fuel would not fill up a single football field above 10 meters high. That's how big the problem is. Now, it's easy to spin it. It's easy to make it sound horrific and mountainous and voluminous. But when you think about how much you get and what the price is in terms of used nuclear fuel, it almost looks negligible from that perspective. It almost looks negligible in terms of the price that we pay because of energy density. It comes down to energy density. Now, a lot of people can look at those casks and think that these things are terrifying because you don't know. Well, what is the process to legally be able to put used nuclear fuel into one of these casks? You have to demonstrate this. You have to take that design and you have to go and drop it 30 foot onto an unyielding surface on its weakest points. You do a finite element analysis and you say, what is the weakest point on this cask? Lift it 30 foot, drop it, bam, onto its weakest point. That's the first thing. Then you take that exact same cask, and it's a 40-inch drop onto a steel bar. Again, its weakest point. Wham! And then you have to submerge it in fire, almost 1,500 degrees for half an hour, and then 50 foot underwater for 8 hours. Now, this is the same cask sequentially going through all of these, and after every test, it can't leak. And what this is simulating is the worst hypothetical accident condition that you can imagine. Basically, you have a highway accident, one of these things rolls off the cliff. It goes off of a cliff, wham, onto a big boulder. Off that boulder, it rolls off onto a spiky boulder, wham, onto that spiky boulder. But now it rolls into and it has to be exposed to a tunnel fire. There was a tractor trailer hauling combustible fuel fluids, and whatever accident triggered all this, it's a fire, and it's in the tunnel. And then in the process of getting it out, it falls into a lake. And so with all of this, it can't leak. And if you can do that and make it so that it won't leak, you can get a license to build them. But it's got to pass it. So they are destructible, but they're virtually indestructible. And the reason why that's significant is that technically, if one of these things is virtually indestructible and somebody wants to throw bombs to terrorize people, as a nuclear engineer, as a health physicist, as an expert in radiation safety, I would rather they bomb these than an occupied building.
Yeah. Wow.
I would much rather you scare people by rolling these things down the highway than putting a bomb in a place where people are. In other words, I personally would prefer people to be scared than dead. Because you can kill people with a bomb, and you can scare people with one of these, because they are that tough. They've shown demos where you actually shoot a missile at one of these things, and you damage a missile, and the missile explodes. Now, another concern that people have about nuclear energy is, well, what about the waste? Where are you going to put it? We don't know what to do. We've had 50 years of trying to solve this problem. We never solved it. Well, one of the least known facts about nuclear waste is where I used to work, Waste Isolation Pilot Plant. It's a deep geological repository for transuranic waste in southeast New Mexico. It was started being built in the 80s, and it got its license from the Environmental Protection Agency in 1999 to dispose of transuranic waste, plutonium mainly, contaminated waste, that requires geological isolation. And it's been running with an amazing record. And we're going to talk about here quite shortly the worst thing that's ever happened at the Waste Isolation Pilot Plant. And that's where you can see it's located, right there in southeast New Mexico. And here's a look at what it is. It's basically, there's a salt deposit that's probably about 2 or 3 times the cross-sectional area of Oklahoma. And right where the width is, it's about a mile thick. Water evaporates. So the top layer is almost pure sodium chloride, and then it's mixed below between calcium sulfate and sodium chloride. Basically, if you have an ancient lake and everything, and the water evaporates, what deposits on the bottom? All of the stuff from the living tissues that turns into the calcium sulfate, the clams or whatever, and lots of sodium chloride. There's also some potassium chloride, but it's water evaporates, and it's about a mile thick. And so the geologists tell us this is almost the quintessential example of what they would call geological stability. That means whatever's happening in terms of plate tectonics, this is ignoring it. The salt is elastoplastic. It basically heals itself. At these depths, basically about half a mile down, it self-heals. The salt crystals will slide on their grains under the massive lithostatic pressure that's taking place, and it will just heal itself as it goes. So you don't get any faults, you don't get any geological activity. So the idea being, because of that, the radioactivity literally will just decay down into a different kind of dirt before it ever sees the biosphere again, if ever. And the sun may go red giant before that happens, it's possible. So in 2014, and I published this in 2016, in 2014, the Los Alamos National Laboratory sent a drum that, for all intents and purposes, exploded. 7 curies, that's actually a lot. 7 curies of americium, it's a transuranic radionuclide, was aerosolized. And the funny thing is that the safety systems worked. The detectors found it, they shifted to filtration, and the HEPA filters turned on, and this resulted. That's the release that occurred. Now we see the green glob. This is actually what Lawrence Livermore National Laboratory published. This was part of the consequence assessment that we did right there, and so I published their result. They chose green, don't ask me why, but that was the official result of the release. Now that looks really scary. That looks really scary. But let me put this in context. There were about 500 atmospheric thermonuclear tests in the past century by the nuclear weapons powers. And they covered the Earth with fission products, including americium. Now, this was many, many years ago, it was the past century. But when that occurred, there was americium that was deposited there from atmospheric weapons testing. United States included, but also Russia and China, France, Great Britain, the weapons powers. They're all guilty of doing that. And the amount of americium that was deposited there was comparable to what had already been put there in the previous century. That's the level of safety that was designed into mitigating this event. Now, nobody had believed that this would ever happen, but it was designed to mitigate that should it occur. This was considered beyond extremely unlikely. Why would Los Alamos send a drum that would explode full of transuranic waste? That made no sense. Nobody believed that would happen, but it was designed in case it did. And even though the safety systems worked, this literally would have been within the license that EPA issued. So all nuclear facilities have a license on how much radioactivity you can release. We'll talk about that later, what those numbers are, so you can get that in context, so that it's not just some horrific fact, but you understand the risk that's associated with that. And this was about 1% of their license limit. So if this had been planned and it had been controlled, it would have been a negligible fraction of their annual release limit. Doesn't mean it didn't terrify people, but we'll get into that when we talk about radiological risk in context. What are the risks? And what was the risk of this, even though it's this big green glob that looks really scary? Another issue that people have is, well, who's going to be around in 10,000 years? It's fine that you got the whip, right? That's great. But who's going to be around in 10,000 years? You know, how long does human recorded history go? 10,000 years, but you want this to be there for 100,000 years, for a million years? How do you know what's going to happen? How do you know it's going to be safe? Well, the nice thing is that Mother Nature told us how to do this. How to do geological disposal of used nuclear fuel. There's a place in Gabon, in Oklo, Gabon of Africa, where there was a uranium mine. And at this uranium mine, they found that the fissile component of the uranium fuel, the uranium-235, was depleted. It didn't have the same natural fissile content that you have in regular uranium, that you get anywhere else on the planet. It was very weird. And to put in context just how crazy this was, I'm going to show you an example of natural neodymium. If you look at neodymium, or any of the other rare earth elements, if you look at those, the elements that were found there at the Oklo site, natural neodymium has an isotopic distribution. That means that even though it's got 60 protons, it's got different numbers, it can have different numbers of neutrons and still be stable, not be radioactive. And that's what this bar graph up here shows you, is the relative abundance of all of those different isotopes. Now, to give you a little bit more insight, if I average all of those, do a weighted average of those, I get the average weight of neodymium is 144.242. That's because you're averaging is 142 and 143 and all of these in a weighted average, and that gives you the what's called the atomic mass. It's a metric for how much mass do I have if I have one atom of neodymium. And on average, it's going to be that number right there. So if I have a neodymium sample, that's going to be the atomic weight of the neodymium. And it's because of this isotopic distribution. What is the distribution of stable isotopes in that particular element? Well, that's not what we found at Oklo. What we found is this crazy thing. It looks like this. Nowhere on Earth. And all of the isotopes that have fission product terminal elements had these same kind of crazy distributions. It wasn't like what you saw anywhere else on the planet. Well, a couple of scientists put it together, and this was when it was published in Scientific American. I also published some fun stuff on this, which I'll talk about here in a second. If you look at the neodymium from the terminal distribution of isotopes from neodymium from used nuclear fuel, it looks like this. And if you subtract off the natural neodymium distribution from what you have in Oklo, you get this distribution that, for all intents and purposes, is statistically indistinguishable from terminal fission product neodymium isotopic distributions. In other words, the neodymium and all of the other rare earth elements were a superposition of terminal fission products. Because what ends up happening is that uranium-235 has got a shorter half-life. The fissile component of uranium has a shorter half-life than the non-fission fissile component. That uranium-235 is 0.7% of uranium, and it's got a 700 million year half-life. Now that's not short. But when you look at the non-fissile, the uranium-238, that's got a 4.5 billion year half-life. That's the age of the Earth. That's a lot longer. So 700 million years does look kind of short compared to 4.5 billion years. That's a lot. 4 billion years is a long time. And radioactivity exponentially decays as you go forward in time, which means it exponentially increases as you go backwards in time. And what that also means is that if you go back about 2 billion years, uranium-235, the fissile component, it wasn't 0.7%. It was about 5%. So you go back about 2 billion years, natural uranium would have the same enrichment as commercial nuclear fuel does today. And so if I had a concentrated ore, right, geology brought this stuff together, through magma and through water and all these different processes, erosion and so forth, and it concentrated this uranium. There's a place where water was able to make this thing go critical. So over millions of years, Mother Nature made her own nuclear fission reactor. And she disposed of the used nuclear fuel in a stable geological formation so that it literally decayed down into a different kind of dirt before it ever saw any element of the biosphere again. And so, why reinvent the wheel? And that's why I did this research here. If you look at the title, it kind of speaks for itself. If you look at the physics there, natural nuclear fission reactors are, for all intents and purposes, ubiquitous throughout all time and space. Because this process that allowed this to occur, basically neutron star mergers, would have been occurring since very shortly after the Big Bang, and making this stuff and seeding these very same processes. And so we know what to do. It's called stable geology. Modern geology works, and we have some very poignant evidence. And specifically, this research right here shows us that there's this thing in physics called the fine structure constant, which means that the constants of the universe that define the strong nuclear force, electromagnetism, and the weak nuclear force, that they have been the same, as you can see from the fission product terminal. All of those constants go into nuclear fission. Those constants have been the same for billions of years. This is some of the most poignant physics research that relates to what we're talking about, is what this means about how the universe behaves long term. All right, so we're talking about radiation. Where does it all come from? What are all of the sources for radiation? There's a lot of different sources, and they're not all equal in terms of the risk, or more specifically the dose. The risk is in the dose. So there are a lot of sources for radiation in our society and in our life. Where does it come from? Well, half of it is from nature. The other half is from medicine. The biggest fraction from nature actually comes from radon and thoron. Uranium and thorium, they decay down into radium. Radium only decays into radon. Every breath of air you've ever taken has been radioactive. It's had radon, natural radon. You've never had a breath of air that didn't have radon in it. It's always been radioactive. And that's where the biggest chunk of natural radioactive dose comes from, is from radon. Well, a little bit comes from space, and a little bit comes from the Earth. Some of it comes from potassium, naturally radioactive potassium. You die without potassium, and it's naturally radioactive. And you get dose from that. But then there's also nuclear medicine, radiography, fluoroscopy. You can do some magic stuff with that. Stuff that years ago would have taken exploratory surgery, you can do almost in outpatient. I personally have had a stress test. I walked in perfectly fine, and I walked out with a Band-Aid. That's the kind of magic where you can do treatment and you can do diagnosis outpatient, where the person walks out with a Band-Aid on their arm. Treatment that otherwise would have required cutting somebody in a hospital bed and stay. This stuff is like magic. And the physicians, they do the same thing. It's risk versus reward. You don't want to cut somebody. You want to give them a good health outcome. But like with any medicine, there are side effects. You've just got to have a bigger reward than there is the risk, and it's got to be substantive. All right. So if I told you that yesterday, that you were exposed to 10 to the minus 5 joules per kilogram of radiation dose. What is that? That's gobbledygook, right? That is gobbledygook. Was it any different if I say you got a millirem? What's a millirem? You don't know, right? So if I tell you got a millirem, that's like, you might as well say 10 to the minus 5 joules per kilogram. It's still Greek. So let's talk about that. 1 millirem is what you get from natural radioactivity. Radon, thoron, uranium, potassium, thorium in the earth, all of their decay products, potassium in your body, cosmic rays from outer space. You get about a millirem per day. So that is the first nugget. And we're going to come back to that. There's a reason I picked this. And we're going to go over logarithmic orders of magnitude. And we're going to say, what are the consequences, what is the risk, and what is the public perception? That's really what this is coming down to, is to be able to make a risk-informed decision. What is the risk? What's the risk of a millirem? How afraid should you be of a millirem? How concerned, if you had a millirem, should you be? Well, let's talk about it. So to start off with, 1 millirem. That's going to be our fundamental unit to put things in context. That's what you get because you're alive. Because you're living and breathing, that's the price you pay. You get about a millirem per day. And that's on average for the US population. 5 millirem. So if you do coast to coast, LA to New York and back, you get about 5 millirem. Is that scary? Take a coast to coast trip, 5 millirem, 5 times your annual. This is going to be from cosmic rays because you're way up high. You're not being shielded from cosmic rays anymore. That is the annual limit from the EPA on drinking water. So remember, the Earth is radioactive, and some water comes from places where you're going to have a little more radium than others. the amount that you can have of radioactivity in the water cannot give you more than 5 millirem per year for it to be legal. Otherwise, it's got to be mitigated. Now, that makes it sound scary. There's a regulatory limit. If you found out that your water busted the regulatory limit, that's pretty scary, right? You might get upset. You might get vociferous. You're going to have a visceral reaction if you find out that your water does not meet regulatory requirements for radioactivity. That can be terrifying. Agreed? That could be terrifying. Well, that's the limit. It's about 5 millirem per year. We're going to keep going up orders of magnitude. This is going to be logarithmic. Let's do 10 millirem. If you're a small, petite female or a child, the minimum dose that you'll get in a year from internal potassium is 10 millirem. Because potassium is naturally radioactive, you need the sodium-potassium pump, you need more potassium in your cells and more sodium in the intercellular fluid in order for your chemistry to work right. 10 millirem is that internal dose that you get. That's the minimum that you can get. And yet that is the off-site EPA regulatory limit for nuclear facilities. When I showed you that graph of the WIP, the Waste Isolation Pilot Plant, that was the limit that they were a small fraction of that terrified people. 10 millirem. It was about 1% of that. Terrified people. And not because they were a long ways away from the regulatory limit, but because it was a nuclear waste repository that leaked. That was what terrified people. How do you contextualize that? How do you react to that? How do you keep yourself safe if you found out that happened? So that's 10 millirem. Keep going up. 40 millirem. Now, because the potassium is what's in the cells, potassium content scales with muscle content. More cells. So if you're a large muscular male, you're going to get about 40 millirem. So if you want to be healthy, if you're strong, Herculean dude, that's about the price you're going to pay. You're going to get about 50 millirem to be healthy from internal potassium. Keep going up. 100 millirem. We scared yet? 100 millirem. This is what you would get for a hip x-ray. So if you've ever had a hip replacement, this is the minimum that you're going to have, is about 100 millirem, just for that x-ray. That's about the dose that you get. That's the dose to the public from any nuclear facility. So if you're a hospital, if you're a university, or if you're a nuclear reactor making electricity. If a cowboy decided he wanted to go up and put a tent on the fence, or a homeless community decided to go ahead and surround you, by law, they cannot get more than 100 millirem per year. That's the maximum dose that you can have at the fence. That includes those interim spent fuel storage facilities. Those big casks, that fence, it's a fraction of natural background because natural background, on average, is about 320 millirem per year. And so 320 millirem per year is what you get on average, and this is based on population, so actually if you live on the Colorado Plateau, it's going to be a lot higher. But on average, you're going to get about 320 millirem per year, something on that order. That's why about 1 millirem is about the daily dose. Let's keep going up. So if you're an older guy like me, you've had a stress test, right? Where you literally walk out with a Band-Aid on your arm and a pinprick in your arm. You get about 1,000 millirem. Now I told you I used to work on the NEST, the Nuclear Emergency Support Team. 1 gram to a member of the public is the minimum dose that a member of the public would have to be able to get in order for the Environmental Protection Agency to recommend to a governor to evacuate. That's got to be scary, right? Be told to move. I mean, that's got to be extreme, right? Move from your house. That's about the dose you get if you've done a stress test, or if you've had a CT scan to the head, chest, or hip. It's about 1,000 millirem, something like that. That's enough to cause the emergency services to ask you to move permanently. You scared yet? That's got to be scary, right? I mean, if that's not cognitive dissonance, I don't know what's going on. Move from your house permanently. Exclusion zone. That's terrifying. Exclusion zone. That's what we're talking about. What does it take for an exclusion zone? And then, if that's not bad enough, if they do it, trigger this, it's only got to be 500 millirem per year after that for you to permanently be removed from your home. just right above natural background, is enough for an exclusion zone. Let's keep going up. 5,000 millirem. That literally is a legal dose to a radiation worker in the United States. Are you scared yet? So if you're a rad worker at a nuclear facility, legally you can get 5,000 millirem in a year. I don't know. I mean, if you're scared at 1 millirem, we're 5,000 at this time. Are you scared? I don't know. This is a safe worker for rad workers. It's considered based on OSHA standards for the risk that you incur for having a job, for being paid, an acceptable risk. Meets the standards. That's assuming what we'll call linear no threshold, which we don't even talk about. But that's considered a safe work environment. Let's keep going up. Because finally, going up this logarithmic scale, finally we hit something that we can say, all right, I finally hit a threshold. At 10,000 millirem, there's like 1 or 2 journal papers that show that this is likely the threshold where you can actually detect a measurable medical effect. All that stuff up there has no detectable, measurable medical effects. If there are effects at all, they're too small to see. Now, that's worth thinking about, right? I can see a scratch. I can see a rash. I can see a sniffle or a cough. But if I can't see something, we're going to come back to this. How much time, money, fear, and anger is worth something that you can't measure? In the United States, apparently billions of dollars, literally, billions of dollars for something you can't measure. But this we can. At 10,000, this came from radiotherapy of children, that you can get secondary cancers at about 0.5%. You raise your cancer probability by about 0.5%. Now, total cancer probability, if you live long enough, it's about a 40% chance you're going to get cancer. You don't die from something else, you're going to get cancer with about a 40% probability. So that kind of helps to contextualize what's 0.5%. It's a measurable increase in your natural cancer probability. We just hit. All right. 100,000. That's 5%. These kinds of doses, we know this from atomic bomb survivors. That's basically where you get these doses. The atomic bomb survivors taught us that. So that, again, 5%, that's measurable over your natural 40% probability. All right, 500,000. Now you can be scared. Now, as a health physicist, I would say that's scary. Reason why? Because at 500,000 rem, this is what we call lethal dose. And what that means is that if you get this kind of dose, half of the people that get this dose will die from acute radiation syndrome within 30 days. You need to be in a hospital if you get this. Now, if you get to be a hospital, you're going to be fine. The person that gets this kind of dose, within 2 weeks, they're going to be like a later stage AIDS patient. Your immune system has gone. You just irradiate that red bone marrow so much that your immune system isn't there. And if you don't have an immune system, you need to be in a hospital bed. And so that's scary, because you do need to be in a hospital bed if you get this kind of a dose. You need a hospital bed. You need antivirals, you need antibiotics, you need antifungals. You need to be monitored because the simplest opportunistic disease, you don't have a defense. So that one's scary. So now that's a scary dose. Although all the way up at 100,000, that's where you start to get acute radiation syndrome, but the survival rates are much, much higher. You're just going to get sick, and unless you already have comorbidity, you're likely just going to be fine. You still want to be monitored. I would say that's kind of like COVID. You're going to be sick as a dog. You're going to feel horrible, but you're probably going to recover. So that's scary. This one's terrifying. Lethal dose. You still might survive, especially if you get in a hospital bed. And then finally at 1 million millirem, now we're talking hospice. You're not going to survive from an acute dose like that. It's never been seen. It's got to be protracted, meaning it's got to be over a long period of time, and then you can survive that kind of a dose. All right, so let's put this in context. all of these up here, all of these doses up here, have no measurable medical effects. If there's an effect, it's too small to see. It's not until you get down here that you can see it. And so now I bring back that point. If you have something that's a hypothetical effect that's too small to see, how much money is that worth to avoid? How much time? How much fear? How much effort is that worth? Personal decision. You can decide for yourself. So it's a what if. What if there is something? Well, what if there is an effect? Okay, fine. There might be, but it's too small to see. So let's just assume that it's there. It's too small to see. How much of your time, effort, and money should be thrown at it? With the whip, it was a fraction of this, and that cost the United States $2 billion to avoid that. I can think of a lot of things I'd like to do with $2 billion. It wasn't going back and making whip no longer be able to release on that order of a dose per year. But that's what we did in this country. And we'll look at some other examples as well, as the kind of money we throw at trying to mitigate this, right? 5 milligram, right? That's the drinking water standard. That'll terrify people if you bust the EPA's drinking water standard. Or if you find out that a nuclear facility busted the 10 milligram limit. How scary is that? That'd make headlines, right? 10 milligram. But how much further down 10 milligram is it? That's 1,000 times lower than the threshold for anything measurable. 1,000 times lower than anything measurable. But that would evoke visceral reactions if you found out that any nuclear facility busted their EPA regulatory limit. That's the way we do nuclear. That's how we do nuclear energy. The design specification that I teach my students, you can ask any of them, I have them here, is that we design it so that the absolute worst thing that could possibly happen is that nobody gets hurt. That's the design. What you've seen with the cast, with the whip, with nuclear power plants, as we'll see, that's the design. The worst thing that can possibly happen with an American design is that nobody gets hurt. That's how much money we throw at it. All right. Well, how much is there in the environment? I had mentioned that uranium is more abundant than tin, but it has heterogeneity, like all materials. So you can see here that the maximums that we have is about 3 parts per million of uranium. And you get a bunch of it across the United States. You don't have a whole lot on the coast as much as you have up around the Colorado Plateau, but you get a lot of gradients. Now that's 3 parts per million. That's actually more than you have for tin. I've heard one of the arguments against uranium is that it's a limited resource. Well, so is tin. But there's a lot of it. It's actually quite abundant. And there's a lot of stories that go out there that we're going to run out of uranium. We're not going to run out of uranium. Because of this, there's actually about 4.5 billion tons in the ocean just from natural runoff. And it's continually being replaced year after year and plating out on the bottom of the ocean. Also being refueled a little bit by hydrothermal vents. Thorium, that's a popular one. It's about 3 times more abundant. You can see again on the Colorado Plateau. Potassium, again, lots and lots up on the Colorado Plateau. Dose rates are going to be a lot higher from terrestrial radiation. And then from outer space. You can see again on the Colorado Plateau it's a lot higher. But out west, it's pretty sparse. You don't get a lot of people out west. And so the doses, that 320, is mainly these coasts where you're going to get lower dose rates as a general rule. So that's these sources that we have. Why is it that renewables are so important in the modern conversations that we have around the country? There's these kinds of things, life cycle emissions. Well, what I want to go over here, some of my research, but I'm actually going to use data that came from United Nations. I'm going to focus on them and other researchers in terms of how does our love for our planet, and I love what Scott said, right? I mean, I think we as a culture, we recognize the importance of nature, right? That's why we have national parks, where by law, the only thing you can do is look at it. We went to the zoo yesterday, same kind of a concept. They're for looking at. They're not for going up and petting and touching and poking, they're for looking at. And that's the point, is that there is value that. We esteem that. So let's look at what are these impacts that we have. We've gone over radiological risk, but let's look at the rest of the impacts. So this came from the United Nations, and the main reason why renewables are being focused on is because of greenhouse gas emissions. That's really it. It's greenhouse gas emissions. And if you look at nuclear, it's less than all the others. Max and min. If you want to remove greenhouse gases, if that's really your priority, it's nuclear. And the United Nations knows this. The energy experts know this. It's not a secret. Nuclear doesn't. It goes critical and makes heat from fission reactions. And so if you were serious about reducing your greenhouse gas emissions, you're talking nuclear. Yeah?
Why is the hydro 360 and 660 so different?
It's going to depend on the different designs.
They're that big of a difference?
And it's based on countries. So these are they're the infrastructure that you have integrating it into those countries.
Okay.
So that's what these are looking at, is looking at all these different countries and how they would be integrated for all of these different technologies. And you can see max and min, either way you go, is lower than all the others if you go to nuclear. Even though the worst case for nuclear is better than the best case for any other country, for any other technology.
As I recall, the report explained that, as I've read that, you have to also look at the word life cycle and think about, like on dams like Hoover and Bonneville and so on and so forth, where it took 10, 15 years and an awful lot of diesel trucks to build, versus a small hydro in Rhode Island that might have taken a couple of months.
It's the price you pay. What is the price you pay for greenhouse gases? Yeah, for life cycle greenhouse gas emissions. Well, Scott talked about the impact from mining. Mining is pretty dangerous. I used to work in a mine. The waste isolation pilot plant is a salt mine. I was a certified miner in New Mexico for many, many years. And what are the impacts, right? If we like to have pristine earth without seeing these mine tailings and these open pit mines, those, I would say it's scars on the earth. We want to have as little mining as possible. And specifically, those of the rare earths. What are those critical minerals? The ones that are hard to get, that aren't abundant, that you can't just throw a lot of energy at and make something like, fertilizer or concrete, which take a lot of energy. And that energy has to come from somewhere. If you look at nuclear, you really don't get beat unless you're talking about hydro or combined cycle natural gas. How much mining do I have to do? And then there's all the it's not just the environmental impact, but the mining, the milling, the manufacturing. That has industrial accidents. Those people, people die from those, hopefully at a negligible rate. Is it possible to be negligible in deaths? Well, you can certainly be the least. And that's a good place to be, which is what we'll find later, is basically where nuclear is, for all intents and purposes. So you can't say it's zero, but you can say it's the smallest, which is pretty impressive and very attractive. So how do we minimize having to dig all this stuff up? How much earth do we have to move in order to maintain our standard of living? You want it to be small. How much land am I willing to take? I've heard people say, well, there's lots of desert, we can cover that with solar panels. Is that what we really want to do? Is we want to say, well, there's unused land? What is unused land? I'm taking that ecosystem, I'm saying I'm going to use that for energy. That ecosystem, whatever it is, I'm going to devote that to energy because there is no other human application for that, so therefore we're going to give it a human application. You choose to do that, it's your land to do it, that's your choice. Me personally, I like to take as little land as possible, and energy density does it. That's why we like fusion. High energy density. Same thing applies with fission. High energy density. The exact same physics that make fusion attractive are what make fission attractive. High energy density. And this is a logarithmic scale. So every time I go up one of these, it's a factor of 10, like we did with risk. Factor of 10. So that if you were looking at photovoltaics, it's 100 times more land. That no longer is whatever it was, whether it's agriculture or forests or open desert, whatever it might be, or abandoned fields. You want to take up the smallest footprint. Like what Scott said, you want a little postage stamp supplying millions of homes. That's what it is. That little postage stamp supplying millions of homes instead of having many, many miles of coastline being devoted to energy through wind or solar. You just do the postage stamp. So this one's an interesting one. If you're talking about mining and milling and all those precious minerals and all of the processes that you have to go through, the acids, the leaching, the bleaching, they did an assessment. They said, what's most carcinogenic? You know, solar panels, they'll have PFAS in them. They'll have cadmium, arsenic, all these elements. And they said, well, if we talk about carcinogenic potential, how does nuclear stack up with all the rest? And the argument is because you need to do so little. There's so little that you need to do because of energy density. And you look at all the toxic materials, not just with nuclear, but with all energy technologies. Nuclear, again, it beats them all. The worst case for nuclear is better than the best case for anything else. Energy density. So yes, there is toxic materials that are there. Yes, there is carcinogenic materials that are there. But you just need so little of them. Remember that football field? What was the toxic potential of a football field versus all of the other waste from all of the other options? That's what this is comparing. Well, how bad is that football field? Just how much risk comes with that football field of waste to give us 20% of our electricity for 50 years? Now, there's two ways of looking at safety. This is deaths from accidents, right? So if I'm doing wind and I fall off of a big wind turbine, that's an accidental death that occurred from wind. If I'm doing solar, I'm installing solar and I get electrocuted and die, that's an accidental death. Now, you don't want to trivialize that. Same thing with nuclear. You don't say, well, one death doesn't count because it's from an energy source I like. What you do is you say, what were the deaths per gigawatt hour that were incurred from these different energy forms? And one way to do it is what was done here with this Our World in Data, where if you include Chernobyl, you say, we're going to include Chernobyl, all the deaths from Chernobyl. We're going to include Chernobyl in all the deaths. Nuclear is safer than wind. It's right between solar and wind if you include Chernobyl. Now, there are other researchers that have said, that's like folding in the Hindenburg with air travel accidents. It doesn't make sense to say we're going to include the deaths from the Hindenburg with air traffic safety. They're completely different technologies. They're completely abandoned. It's not going to happen again. You can't have another Hindenburg because we're not making another Hindenburg. And if you do, then okay, maybe we'll consider it. But for now, there is not going to be another hydrogen Zeppelin. We know, we learned our lesson. We're not going to do that. And so if you take Chernobyl out, as was done by the Europeans, nuclear is an order of magnitude safer than even solar. Why is that? How could that happen? What about these nuclear accidents? This was a question that came up. What about the nuclear accidents? 3 Mile Island. Now, 3 Mile Island was the reason why I picked that point of 1 millirem to start off radiological risk in context, because that was the consequence to the average member of the public. All of that fear, all of that stress from 3 Mile Island, the actual risk was about 1 millirem, about what you got in a day. So if it all happened in one day instead of over a week, that natural background dose would about double that day. But it was only a fraction of that because it happened over a week. But how much fear, how much money, how much time, how much effort had been expended over 3 Mile Island? Basically upgrading things cost many tens of billions of dollars. Making sure that never happens again. That's how we do nuclear, remember? The worst thing that can possibly happen for our design specification is that nobody can get hurt. Like that cask, like this Western. All right, well, hey, Fukushima was a Western design, right? They took the design from us, and they did that. But I pointed out that evacuation is triggered at about 1,000 millirem. Internationally, it'll be triggered about 2,000 millirem. It was triggered for Fukushima conservatively. They averaged less than that. So it's something like 700 or 800 millirem for the members. And again, that's more than an order of magnitude below the threshold to get measurable medical effects. And to put this in context, the trigger for that was a 9.0 earthquake, basically biblical in proportion, with a tidal wave, again, biblical in proportion, took out on the order of 20,000 people That's not what we think about when we think about that earthquake. We think about Fukushima. 20,000 deaths, basically a biblical scale event. And we think about Fukushima, and if you look at United Nations, World Health Organization, all the review papers, even my research agreed with this, showed that, again, the doses to the public were too small to ever create any measurable medical effects in the public forever. Ever, ever, ever. The doses were too low to have any measurable medical effects. That's just, again, it's a conservative action of that. So that literally, the only deaths from Fukushima were a panicked evacuation. About 2,000 people died because they were terrified. They wanted to get away from that. Think about that. Again, how much time, money, and effort is that 1,000 millirem worth? Remember that scale? Well, apparently it's enough not just for billions, but also to risk and lose your life over, as evidenced by Fukushima. It's enough to risk and lose your life over. That's worth thinking about. Yeah?
On the slide before, or the 0.03 number for nuclear, did that include the people who died from the evacuation, or just the one worker who volunteered to go into the plant?
From Fukushima?
Yeah.
No, this is not from the evacuation. This is radiological deaths.
Okay,
It's
so
not
it's
an
just
industrial
like
death.
okay,
It's not an industrial death. So this is what happens. So if somebody decides to commit suicide, that would not be encountered. It would be somebody falling off of a wind turbine, somebody getting exposed to radiation, or somebody, a slip, trip, and fall on a nuclear power plant. If it's an accidental death, directly related to that. Not because of what you choose to do, but because of what they did at the nuclear power plant. So it would not include the 2,000 from evacuation.
Got it. Just double check.
Yeah. Again, even with the wind turbine, it's the same kind of concept. Yeah.
And the graph on the right does not include Chernobyl.
It does not. That's the difference between the two.
Yep.
As you can see, orders of magnitude.
Yep.
And that's simply because Chernobyl was the lion's share of accidental deaths. So let's talk about Chernobyl. So I just recently published a paper which has some really interesting revelation. Now there's a set of researchers from the European Union, and they looked at a very interesting cohort, the Estonians. The Estonians, during the time of the Soviet Union, was part of the Soviet bloc. And so there were many Estonian men who were part of the Soviet military. And when Chernobyl happened, they took the military and said, go clean this up. They were the liquidators. If you've seen the Chernobyl movie, the people that were actually shoveling the stuff, they were out there and you go out and do a shovel, and then you're done, go away. Go out and do a shovel, and then go away. They got a dose because they were shoveling this core material that was spewed out all over. And the reason why they chose to study the Estonians is because there were lots of Estonian men that were back in Estonia that weren't in the military, and there was no fallout there. So they weren't exposed. But they had the same lifestyle, same age, same food, same behaviors, and you could compare disease rates for the Estonian men that were not in the military at the time with the disease rates from the liquidators that went back to Estonia after they were released from the military. They could say, what was the difference? And in 2023, they found a small statistically significant increase in cancer to the liquidators. Not a big surprise, right? Not a big surprise. Now I'm going to shock you. What they found was a massive 600% increase in suicides. Whoa! Overwhelmingly, the death rate from Chernobyl was from fear. Overwhelmingly, orders of magnitude. So on a small statistically significant increase in cancer. But again, remember what I said at the beginning? 10 to the minus 5 joules per kilogram. Who knows what that is? A millirem. Who knows what that is? But now you've got Chernobyl. You've been exposed to Chernobyl. What does that mean? I don't know. Does that mean if I go bald, it's because of Chernobyl? What if I get arthritis? Does that mean Chernobyl? What if I get a mole? Oh man, who knows what that does, right? Maybe I get a little Alzheimer's. I mean, who knows what it causes? Chernobyl. And what ends up happening, what they showed, people just didn't understand. People don't understand radiological risk. I mean, you do have to kind of go to college to understand it, right? Take a course in it. It's not trivial stuff. Nuclear engineering has a reputation for being hard for a reason. Ask my students how hard it is. Just not while I'm around. The point is, you don't know. You're just a soldier, and you were exposed to Chernobyl. So any bad thing that happens, any kind of normal medical effect, how do you know that Chernobyl didn't cause it? Maybe it did. And if you buy into that, it just compounds. It becomes a self-fulfilling prophecy. And so it's terrifying. And so anytime that something bad happens, it just proves you have no hope. And what do people do who have no hope? And that was just staggering. That more people, overwhelmingly, are dying from fear, like with Fukushima. Fear is the biggest killer. That's crazy. Fear is killing far more people from radiation than actual radiation. It's that bad. That's the
sad,
level.
you guys?
Yeah.
That's sad, right?
Another common misconception, or maybe it's not a misconception, a concern, is terrorism, right? Zaporizhzhia has been being bombed by the Russians. That's terrifying. Hasn't really done anything, but that's because Zaporizhzhia tried to meet Western standards. What are Western standards? A large jet has to be able to go head into the containment, where it's cold, what's holding that nuclear reactor. It's got to go straight into it, and it can't leak. A large jumbo jet has to do a head-on impact, and it doesn't do anything. That's the design specification for a nuclear power plant. Has been since the 70s. So, again, as a health physicist, I'd rather the Russians be hitting Zaporizhzhia rather than the Ukrainian army. Because if they hit the Ukrainian army, they're probably going to kill people. If they hit Zaporizhzhia, they're going to scare people. And it works. It does. It's very effective. But still, I'd kind of rather you be scared than dead. Because that's the design specification from the NRC to get a license to build a reactor. That's how strong these have to be. So they're not indestructible. No, they're not indestructible. They're just really, really impressive. Okay, am I going to be able to play this?
Mm-hmm. If you hit next, it might just start playing.
Was that? So again, the design specification is the worst thing that can possibly happen by design is that nobody gets hurt. That's how we do it. That's our mission when we do design. I have a demo on the back of what hypothetical interim spent fuel storage would look like. This is just a plan view. There's a 3D model that you can go back and look at should you choose to do so. And this is just hypothetically what could happen for an interim spent fuel storage facility. And with that, I'm ready for questions. Did I put people asleep? Ben?
So, if you put one of these storage facilities in your state, outside of just like the development benefits and like the jobs or whatever, how much do you get paid for hosting this?
That would be negotiated.
How much
But
do you want?
that would be negotiated, but I would point out that the money that's on the table, what the DOE is currently spending right now, right? They tax nuclear energy. So we have 3 nuclear power plants in North Carolina, one right outside of Raleigh. So a lot of my electricity, the bulk of it, comes from nuclear, and I pay about 1/10 of a cent per kilowatt hour. And so there's about $40 billion in the nuclear waste fund right now. But the amount that the DOE has to pay the generator sites, it's about $1 million a day.
So that state would make.
Some
at
fraction of
least-
that.
Yeah.
Some fraction of that, if you were to take it all. So I mean, Scott kind of pointed this out. There is substantial potential, should someone choose to do so. And so what I just said tells you why Ryan, Pickering wanted a piece,
What they cast.
if he could get a piece.
In 1997, the going rate was $300,000 a year. And for a small community to host a low-level waste site.
Interesting.
And in, what was it, 2005, 2007, when Waste Management opened up their new site at Andrews, their first year of operation, they grossed $500 million. First year of operation, the 20 years.
So, one of the things I'm gonna ask, when, Fukushima and Chernobyl and, I'm thinking of something else, sorry, let me backtrack again, my brain's not working. Okay. When we bombed the two cities in, Japan, one of the things that they did was that they had some elderly citizens who actually volunteered to go and help clean up some of the waste. Was a study ever done on them and the health effects that happened to them from weapons grade uranium exposure?
You talking Hiroshima and Nagasaki?
Yes.
The only ones I'm familiar with are the survivors of the actual atomic bomb. And that's external. So we have large cohorts of internal. The radium dial painters is a really good example of where we studied a large cohort of individuals who had large ingested doses. And the reason why is because, well over 50 years ago, before we had LEDs, if you put radium in phosphorescent paint, it would glow continually. And so we used that in aircraft extensively because you wanted the pilot to be able to see everything always, even in the dark. They needed to see their instruments. And so if you used this radioluminescent paint, it would always tell them. They would always see their altimeter and their speedometer and all of these things, all of their different instrumentation. Now, to get the radium in the paint, you literally just did that. You did a chemical separation of soil, removing the radium, and then you would dissolve it in the paint, and then it would continually glow in the dark. The half-life on that is like, over 1,000 years. And the radium dial painters, they had these very fine little paintbrushes, and they would whip them with their mouth to get a fine point. And so they had just horrific mouth cancers and throat cancers. And so we have very large cohorts of people, and as well as another large cohort that was in the United States. That was a commercial application. We also have large cohorts from the former Soviet Union. They didn't quite have the same safety standards we did. And at the Mayak plutonium facility, they had a lot of workers there that had large uptakes. And so there's another large cohort. So it's probably the most studied carcinogen by many orders of magnitude relative to any other carcinogen that we know of. So we understand it quite well, to be sure. But like I said, that also includes understanding its statistical nature. For example, it's not until you get up to about 10,000 milligram that you can discriminate it from natural occurrence. And that's just the very nature of how it works.
So I've heard, we know we have about 70 current sites for partially spent nuclear fuel right now being basically at existing plants. I've heard, I just want to confirm that what kind of the end goal of consent-based siting would be to consolidate that into 10 to 12 sites. Is that a fair statement?
Possibly. So this is where, Heather, could you answer that question, or Lisa? Maybe both of you?
About how many sites we want?
So the end goal for collaboration-based siting. I would give a technical answer. I think yours is going to be.
Well, about 2 weeks ago at the ECA forum, the DOE representative for collaboration-based sightings. Stephanie Weir might be her last name. I don't remember quite, sorry. But she said that that was about right, about 10 to 12 consolidated sites across the nation and the locations that make most sense considering railways and such. But where we're at in the process now is they're hoping to get out an expression of interest document by the end of this year. It's not quite like the agreements to sign up or anything, just communities saying that they're interested in continuing being a part of this process.
Okay, so I just get the order of magnitude for how many sites you're going from 70 to 10,
Yeah.
something like that. And then is it fair to say that if we're gonna recycle this fuel, you're gonna move the fuel once to a consolidated spot, then if we're gonna set up recycling facilities, it'd be fair to say that these communities who decide to host these consent-based sites are also gonna be likely candidates for additional economic development that's gonna come from the construction of near-site reprocessing facilities. Is that a fair statement?
I think it's probably, my opinion would be far beyond that. It would be all of the affiliated technology that would come with it. Similar to what happened there in southeast New Mexico. When the WIP site opened up, it paved the way for then the first nuclear facility in 20 decades to get licensed, URANCO, uranium enrichment. And that also enabled, I think somebody mentioned it earlier, Andrews, Texas, which later opened up again. So there was a lot of other affiliated work that came because the community was open to nuclear science and technology. And when they realized that, then all of the opportunities to host that kind of infrastructure and investment came to that community. And so they've been very well paid off, even though historically their economy was oil and gas. And that's largely what triggered it, was because the dependency on oil and gas. If oil prices tanked, then too many of their population were out of work.
So it's
And they
too
said, "We don't like
simplistic to say it's just a siting of consolidation of spent nuclear fuel. It's really far greater. The economic potential, the development, the technology is of one of these sites is far greater than just bring me your waste and put it here.
That would be the expectation, no guarantee, but
Yeah.
it's like what Scott had said, that would be the expectation, because now people that say, hey, I want to, let's say it was a fusion facility, right? But they were they had a radioactive path for that. Let's say they were using tritium, right? Tritium can scare people, that's what's in the Fukushima water, right? That can terrify people. But if you know that this community is open to nuclear science and technology, you might want to start doing a fusion research facility. Or, that's just a random example.
Right, okay.
But that would be the expectation, no guarantee.
Could you explain something to me? I know the oil and gas industry has filed they're opposed to the spent fuel storage in Andrews. And they say that they're worried about the impacts on the Permian Basin. Given the fact that you've got WIP there already, as well as Urenco and the other Andrews stuff, how do those two arguments jive?
It's in, the argument actually occurs in Santa Fe. It's not down there in Eddy or Lee County or even in Andrews County.
Okay.
It's actually in Santa Fe and possibly even in Austin. So that's not where those arguments take place. And the biggest narrative that you find there is that they don't want to be the dumping ground for the United States. They say, when they opened up the WIP, it was based on a compromise. WIP was originally designed to receive also defense high-level waste.
Yep.
So the stuff that came from the naval nuclear fuel, it was designed for that. But the Department of Energy agreed to take that off the table if the state of New Mexico would quit fighting it in court, because that costs a lot of money, delays, right? It's a lot of wasted money. And the state of New Mexico said, all right, we'll quit bringing these lawsuits against you if you'll take that off the table. And when that occurred, that finally allowed them to implement the EPA license, which was issued in 1999, and start operation.
All right, then taking that concept one step further is the idea behind collaborative-based siting, the idea that we'll take waste from Washington State, California, and Idaho, but not from New Jersey and Pennsylvania.
Possibly. It depends on, so for example, let's say a native nation decided that they wanted to do this. They could put those stipulations in there. They could say, we're only going to take things that came from other native lands or that have good relations with native lands. And unless you have good relations with your local Native American tribes,
Guess what?
you're out of luck. But if your local Indian tribes will endorse you, then yes, you can send your waste to us, and we'll take. They can do whatever they want, but that'll be part of the
But it all
negotiation.
becomes part of the negotiation.
Yes.
We've got a question.
Oh, sorry.
This one's kind of like less technical, but as you're talking about it, I'm like, what do you think it is from maybe a psychological standpoint or a human experience that makes radiation so fear-inducing?
So, like I said, but Chernobyl, right? You don't know, right? Radiation, by the end of the day, you will have absorbed in your body about 10 to the minus 5 joules per kilogram on average as a citizen, right? Until you know, you don't know. And evolutionary theory tells us that your fight or flight's going to kick in for a risk, and you're going to assume the risk is as bad as it could possibly be as the only way to guarantee you're safe. So if you hear some noise, you're programmed, whether you like it or not, you're programmed to think that's as bad as it could possibly be. The bear, right? Could just be a squirrel falling from the tree. But if it sounds anything like a bear, you're programmed to think that's a bear. And what do you do if that's a bear? Right? Fight or flight kicks in. And you don't have a choice. You're programmed that way. Because you don't know, right? You don't know what that was, but you're going to make that assumption. It's as bad as it could possibly be, and I'm going to react accordingly. That way I'm safe. If it's not a bear, fine. You know, I just did, a record mile. Okay, you did a record mile. But if it was a bear, hey, you're still alive. And so you're programmed to default to that when you don't know. And this is not like I mentioned before.